Okay, welcome back. I am here doing another Mathematica tutorial. This is the 6th tutorial and the same problem sheet, so I'm now on question 14. Okay, so let's begin. Write a comment, question 14, and now let's have a look at it. So it says, verify computationally that for all primes p between 3 and 100,000 that p is congruent to 1 plus or minus 1 modulo 6. Right, so this is a well-known statement about prime numbers, primes greater than 3, that they're all either plus or minus 1 mod 6, and that's easy to prove. But the point of this exercise is to show you how to verify things computationally. Right, now I've got the code written out here that I'm going to write, but I want to talk about it along the way. So I'll just talk about how this works. Okay, so first of all, let's just choose a prime number, like for example 17. All right, 17's prime. Now if I want to check the remainder when I divide 17 by 6, right, we can do that with the mod function. So mod 17 comma 6, let's have a look, shift and enter, and I get 5. All right, so you're wondering, why does that not say plus or minus 1? Well, 5 is 1 less than 6, right? And so that is the same as minus 1 mod 6. Right, so when you use a mod function, you will end up getting a number between 0 and this end number here that you're taking it when you divide it by. Okay, so that's what the function outputs. All right, so let me just show you that this is true. So if I put in minus 1 mod minus 1 6, the remainder of minus 1 when you divide by 6 is 5. Alright, so now that we are content with that, let's choose another prime, 19. For example, 19 is congruent to 1 mod 6. Alright, so this claim up here seems to be true so far, at least with these two. True generally, and so how do we do this computationally? Okay, so rather than a particular prime, I want to do this with an arbitrary prime. So just put a p there. Now p is blue, so it's not in memory. All right. So now I want to give it a value and sort of tabulate over a prime. So if I say p equals prime, and I'll put a bracket, so I'll put in a j. Right. So what this does, this gives me the jth prime number. All right. So just to show you how this works, let's change it from j and put in the 25th. Okay, so this should give me the 25th prime number, 97. Okay, there you have it. The 25th prime number is 97. So this is the simple built-in function prime. All right, and so now that I have that, I want to go back to letting it be the arbitrary the jth prime number. So j is blue, so that I can now tabulate over j, and I get the jth prime number out of this function. Okay, I'll put a semicolon because I don't want to see the output. Right, and now this remainder, upon dividing this by 6, let's give that a value and call it q. Right, so q is equal to this. All right, now I can tabulate over this and get the values of the remainder, right? Okay, so let's see, I want to clear the value of p. All right, now it'll give me some kind of expression. That's fine, that's what I want. I want a general expression. Okay, now I can tabulate these. All right, so table Table is just an easy way to make a list. Alright, so if I tabulate, and now I put tabulating over j, so j goes from 1 to, let's go to the 100th prime, and let's see what we get here. So I'll shift enter. Alright, now you'll see a list containing numbers, integers. The first one is 2, the second one is 3, the third one is 5, and 1, then 5, then 1, and then we see a lot of 1s and 5s, okay? So 1s and 5s are agreeing with the conjecture so far, because 5 is congruent to -1 mod 6. All right, now remember this statement up here says for p greater than 3. All right, now this is true for all primes. All right, so but this says evaluate this computationally. All right, so you've got to stop somewhere when you evaluate something computationally. Okay, so in this case, I don't want to bother checking the first two, right? Because, well, we can see that they have different values as remainders upon division by 6. All right, so I want to start at the third prime. Okay, so we'll start from 3 to 100. Okay, that's good. Now, sure, so this is evaluating this computationally, but I don't want just a list of, say, around about 100,000 numbers, right? I don't want to have to check through that manually to see whether or not this is true. Okay, so we want an if statement now. Okay, so I'll put a semicolon around this. After that. And now I want to put if q. Now I'm putting in sort of a question, right? So I'm not setting the value equal to, if I'm going to put two equal signs. If q is equal to 1, that's a conditional. All right, and then I'll put a bracket around this because I want to add to it. All right, and then I'm writing or. That's a double vertical line, and on my keyboard that is above the enter button. All right, so if q is equal to 1 or q is equal to 5, then I want to do something. All right, so I'll put a comma, and then after that I say what I want to do. All right, so what do I want to do? Put a 1, all right, like a 1 for yes. And then if it's not true, put a 0. Okay, so that should be a little bit simpler. All right, and then, well, look, that's true in every case. So we have 1s everywhere. All right, so that says claim is true for all primes between 3 and 100. But that's a long list so far, right? And it gets even longer if you go up to 100,000. So we must now, well, I want to delete the 0. No, I don't want to delete the zeros, do I? Because I want to check. Sorry, what I want to do is make a smaller list. So around that, I'll put union. Okay, union. All right, so what will this do? This will get rid of the duplicates in this list. Right, so now if I press shift and enter, I get 1. So it's removed all the extra ones in there. So when I see the array containing just the number 1, I know that the conjecture is true for the primes between 3 and 100, because I only have the number 1 in this array. I don't have a 0. I would get a 0 when this is not true, right? So this tells me it's true now. Now all I have to do is increase this to a higher number. So let's change this to 1,000. Still true. Okay, now if I want to set the bounds up above this, I can do that. So I'll put n equals 1,000 there, semicolon, and now I can change this end of the bound to an n. Alright, still the same thing. Okay, now that I know that it works, I can change this to 100,000 and complete the test. Alright, so you can see that took a little longer to execute, but it's given me out just the single digit 1. So that tells me that computationally this result is true. All right, what if I increase it a little bit? So let's add on a 0 at the end of that n. Now we're checking this up to 1,000,000. Should take a little longer. Let's try it. It's going, it's going, it's going, it's going. Right, and it's done. Okay, so it's true up to 1,000,000. If we add another, let's keep going, all right? How long do you reckon that'll take? A while. So let's try it. Shift enter. All right, what did it tell me? The current computation was aborted because there was insufficient memory available to complete the computation. So what's essentially happened is I've constructed a list, right? Constructed a list that was way too long to be held in memory. So when that happens, it will stop the calculation because you're calculating too long. Okay, so that's what happens. Now, of course, there will be ways to do that without requiring to put in a whole bunch of memory, but I'll leave that for another video. Okay, so let's move on to the next question. So I'll go back to a working version of this, and then I'll scroll down and do another question. Okay, new cell. Let's have a look at what we have next. Alright, so this one, the polynomial x squared plus x plus 41 is famous for being simple looking while having many consecutive values of x such that f of x is prime. Alright, so, and then it says disprove the claim that it happens for all of the integers x. Alright, so this is known as a prime producing polynomial. Alright, so I'll enter the polynomial. See, I could enter this as a function if I wanted to, like create a function that inputs x and outputs x squared plus x plus 41, but it's not really necessary. So I will just say f equals x squared plus x plus 41. Alright, shift enter, so now it's in memory. This is in memory as just a polynomial, right? So if I put f, what is f? Well, it gives me back the polynomial, but in reverse order, right? It likes to store things and display them in reverse order. Okay, so now that we have that, well, we can work with it, right? So now what would I like to do? I think I'll use the replace all function here. Replace all f. Okay, x goes to 1. Let's see what we get. So this will sub in the value of 1 there without putting x equals 1 into memory. Okay, 43, yes, that's prime. Okay, so, but why don't we just create a function? Okay, so I'll call it Cindy. Alright, it is a function of x. Module. This is where you put the local variables. Then I'll put f, which is global. Alright, so since I set the value of this outside the function, it's global. And I don't really need anything local, right? Okay, so there's Cindy. And now I want to say tabulate Cindy. Okay, x goes from 1 to, let's try up to 10, see what we get. Alright, so here are some primes, right? 43, 47, 53, 61, 71, and so on. So some prime numbers. Should we check these? Why don't we check them while we're at it? Okay, so now if I'm going to do that, I might include in here, I will include a pair. Alright, now look, I am going to call on this twice. Now I could just write another function to do this, but sometimes, you know, you might compute too much for the sake of a quick answer. Alright, so I'll go with that now. I'll call on the function twice, because I just want to talk about getting a quick answer. So I'll ask the question, is this prime, by using prime q. Okay, prime q, well, it's saying, yeah, here's the number, and then it's given whether or not it's prime. These are all prime. Okay, what if I didn't want to call on it twice? Well, then I could put y equals sim_d of x, for example, and then I would use it, y and prime q y. Alright, and I'll get the same thing. Alright, so for each x, it's giving a new y there. And now what happens if I ask what is y at the end? Well, I get the last one, right? Okay, so that's remembered there. Okay, so now that we have that, what was the question again? Well, that it's prime for all the values of x. Okay, so what we're looking for is a false value. So let's take this to 100 and see what we get. Okay, so there's some false values in there. So now we might ask, when does this conjecture that they are all true, when does it first fail? Okay, so if you have a look here just by inspection, the first time this happens is when the number that comes out of the polynomial is equal to 1681. Okay, and if you want to know which integer did this first occur, and you just want to test that computationally, of course you can do this theoretically as well. But if you just want to do this conjecturally, well, you might include some more information in this, like for example x as well. All right, so we can just go edit that, and I'll do this again, and this will tell us which number that happened at. What was it? 1681. Okay, so it's the 40th one. All right, that's no coincidence, because remember there was a 41 in the constant term of the polynomial. Okay, so that's no coincidence. You can work that out theoretically why it happens there. Okay, so the semicolon and move on to another question, or I'll consider the time, and yeah, let's just stop there, and I'll do more next time. So I'll see you next time. Thanks for watching. Oh, if you don't mind, please like and subscribe. Okay, thank you.